Electric flux, according to electromagnetism, refers to the measure of flow of the electric field through a given area. It is directly proportional to the number of electric field lines that are going through a perpendicular surface. Today, we get to discuss more about electric flux. It's Kisembo Academy, and thanks for tuning in. Now, looking at the illustration on your screen, we are having a surface. The area of this surface, we've labeled that A, and we are having some lines that are going through this surface, and these lines are what we are calling the electric field lines. And like I had earlier said, flux is simply going to be the flow of these electric field lines through this surface area A. Now, if you want to calculate the electric flux that is going through this surface, flux is denoted by that, which is that flux is going to be equal to the E times A. E is simply the electric field intensity of the field lines that are going through the area, and A is the area or the surface area, and that's the formula. So meaning that flux through an area A, which we have showed here, that is perpendicular to the lines of force is going to be equal to E times A. So here the condition is that the field lines should be perpendicular to the lines of force. In this case, they should be 90 degrees to the surface through which they are going through. So now what if these lines are going through this area at an angle that is not 90 degrees? If they are going through the surface at an angle theta, it means that if we are trying to find the flux of these lines that are going through this surface, it means that we're going to have to resolve these field lines to the normal. If the field intensity makes an angle theta with the normal to the plane, then the electric field flux is going to be resolved to the normal. Like we are seeing here, it's going to be E cos theta times A. The cosine of theta is the resolution of these field lines to the normal. So it's going to be E cos theta times the area. It's more or less like previous. Let's look at this diagram here. We are having this spherical ball. It is a sphere with radius. It's having a point charge in the middle, in its center, and this charge is radiating out field lines. The field lines are coming from the center of this spherical ball. So now if we are to consider a spherical surface and we want to find the total flux that is going through this spherical surface, remember these field lines, as they are getting out from the center of the sphere, they are going to collide with the sphere's surface, the spherical surface, at 90 degrees. So it means that for us to find the flux that is going through the spherical surface, it will be the electric field intensity of that point source. We multiply that by the area through which they are going, and in this case, the area is going to be the total surface area of this sphere. And that is what is explained in our next write-up. The total flux is through the spherical surface that is going to be this times that, the intensity times the area. So the electric field intensity times the surface area of a sphere, which is 4 pi r squared, and it's going to be equal to the intensity is q over 4 pi epsilon naught r squared. Multiply that by 4 pi r squared, which is that, and when these common terms disappear, 4 pi disappears with 4 pi, r squared disappears with r squared, you remain with epsilon naught here, q over epsilon naught, and so you find that flux is going to be q over epsilon naught. Q is the charge that is inside the sphere, and epsilon naught is simply the permittivity of free space. And now this relation that we are seeing is what is going to constitute what we'll call Gauss Law of Electrostatics. So what is Gauss' theorem, or the Gauss Law of Electrostatics? This theorem states that the total flux passing normally through any enclosed surface, whatever its shape, is always equal to q over epsilon. If you want more videos, simply subscribe to this channel, and for the benefit of your colleagues out there that would like to watch this tutorial, simply share this video. Otherwise, thanks for watching and hope to catch you in the next video. For Kisembo Academy, this is Arnold Ranga Kuramia.